Yeah, thank you so much for having me. Hi, everyone. My name is McKenzie Carlson. I'm a PhD student at UT Austin here in Texas. And I'm working with Damien Safer here at UT and Laura Wallace at Guillemar in Germany. I'm in the third year of my PhD, so thank you so much for giving me the opportunity to share my work with you. Yeah, as Adina mentioned, I'm going to be talking about triggered and spontaneous slow slip events in the Hikurangi margin today, kind of switching gears from the last couple talks. Um, but I guess we'll dive right in. If you're not familiar with the Hikurangi subduction zone, it is off the east coast of the North Island of New Zealand. And there's a lot of interesting things about Hikurangi, but I'm going to be focusing specifically on the northern part of the margin offshore the city of Gisborne. And here is a great spot to study slow slip events because they happen frequently, they are large, and they are shallow. And for the last 2 decades or so, the onshore geodetic network in New Zealand has been doing a great job at measuring and detecting these slow slip events, and there's been a lot of work done to kind of characterize the behavior of these events. However, despite this great onshore geodetic network, it has limited resolution offshore, and so we need offshore observations to expand our understanding of the processes, particularly out near the trench. It's also a great spot to study not only slow slip events, but the interaction of slow slip events and regional earthquakes. So in this region, there are fairly frequent, moderate to large, magnitude 6 and above regional earthquakes. On this map, I've highlighted one in particular, which I'll come back to in 2021. There was the magnitude 7.3 East Cape earthquake, as well as to the north of Hikurangi in the Kermadec Trench. There are fairly frequent magnitude 7 and even magnitude 8 earthquakes. So it's a great spot to study kind of how these two processes are related to each other. And so to this end, in 2018, 2 IODP borehole observatories were installed. There's a little schematic of what they look like here. They record, among other things, pore fluid pressure, which we can use as a proxy for volumetric strain. And I'll dive into a little bit of how that works in a second. But they're great for measuring transient changes in pressure that we can interpret as formation strain during these slow slip events. So there are 2 borehole observatories. On the map here, we have site U1518. It's about 5 kilometers away from the trench and really useful for characterizing any crustal deformation that is happening out near the trench. And then the other borehole site is site U1519, and that is above a region that has previously hosted slow slip events in the past. And then you'll see in some of my slides ahead, also data from this onshore, this is the closest onshore GPS site as well for comparison. So if you're not familiar with these borehole observatories, this is kind of briefly how they work. So this is what they kind of look like, a schematic. They are installed into the seafloor, a couple hundred meters depending on the particular borehole. And like I said, among other things, they record pore fluid pressure in the formation at various kind of screened intervals where there is a screen in the borehole to allow exchange with pore fluid in the formation, as well as recording the seafloor pressure right at the seafloor. And this makes them super useful for measuring kind of offshore crustal deformation because it allows us to really reliably remove any oceanographic signals from the data. So this plot is showing just a week's worth of data where we have, I have the y-axis flipped here. So this is the pressure record from the seafloor, and then these are the 2 downhole pressure screens. And you can see that in this week's worth of data, obviously the dominant signal here, as with a lot of offshore data, is the tide going up and down every day. And so you can see there's about a 10 kilopascal difference in pressure as the tide goes up and down. That completely dwarfs any of the slow slip event signals that we are interested in looking at. They're often a scale of fractions of a kilopascal to maybe 1 or 2. So with all this oceanographic noise, it makes it impossible to see. But because these sensors are co-located, it actually makes it really easy to get rid of this noise because anything that is happening at the like oceanographically, the tides, eddies, anything else that is caused by oceanography is happening both at the seafloor and is translated into the formation, but then anything that is happening just in the formation is only recorded by the downhole pressure sensors. And so we're able to really effectively remove that oceanographic noise. And so now you can see that the little noise in the data is fractions of a kPa instead of 10. So they're really sensitive to small changes in pressure due to like really small crustal deformation events, small amounts of slip, or anything else that might be going on. And this is useful because we can use these changes in pressure as a proxy for volumetric strain, which we can then use in models to model slip or other crustal deformation processes. And it's fairly simple in concept. When you squeeze the rock, you get a pressure increase, and when you stretch the rock, you get a pressure decrease. And so then we can kind of relate the amplitude of those pressure changes to volumetric strain through a series of equations and some knowledge of the material properties of the formation where these boreholes are installed. And so in order to do that for the Hikurangi boreholes, we performed some lab experiments on core samples that we have to help constrain these conversion factors. And then you can kind of see here, just to show you what those numbers are like, you get 4 to 5 kPa per microstrain, and then you can use that to convert your changes in pressure. Mostly, I just wanted to highlight that this is really sensitive to the particular formation properties. So you can see that between the two boreholes, that these conversion factors are different. So it's important that we have well-constrained material properties, both for calculating these conversion factors and going from pressure to strain. But then that'll also become important, as you'll see when running the models. So in order to kind of show you what our data set looks like, I have this plot here. As I mentioned, the boreholes were installed in 2018 and data were most recently recovered in 2023. So we have about 5 years worth of data. And so this the top two panels here are showing what that pressure data looks like once it has been cleaned up a little bit. So again, the top panel here is showing in pink 1518, that borehole site near the trench. In the middle, 1519, the other borehole site. And then for reference is that closest onshore GNSS station. And so you can see over the 5 years of data that we have, we detected at least 5 slow slip events. There could be other smaller ones in the data that we haven't discovered yet, but there are 5 that are pretty obviously apparent when looking at the data. Most of these correlate really well. Most of the transient pressure signals that we see in the borehole data correlate really well with the onshore GNSS data. And so we can feel pretty confident that these transient pressure changes are due to slow slip events. However, in 2021, following that East Cape earthquake that I mentioned, there is a very dramatic, I promise it's dramatic, it's a little bit hard to see at the scale, but dramatic pressure change at particularly site 1518 and a bit of a signal at site 1519. Which we're interpreting as a slow slip event that happened immediately following that earthquake. However, the notable thing here is that we see absolutely nothing on the GPS, and that's true of any of the other stations as well. So the borehole observatories were crucial for observing this event, and I'll dive into the details of that particular event in a minute. But in order to model these events, we are doing a 2D slip distribution, just kind of along the profile of the borehole observatories, and we're using realistic elastic properties to recover slip magnitude and distribution during these slow slip events. So just a few details on our model. We create Green's functions that relate slip to strain in the boreholes or displacement at the GPS sites in 5 kilometer wide patches of the fault. So we're kind of breaking the fault into patches that are 5 kilometers wide along the x-axis. We're using Pilot to do this, to make these Green's functions, which allows us to account for realistic elastic properties in our models, which is super crucial. It really changes the amount of slip that we are getting out of our models. And so we are using a regional velocity model that was published last year to kind of constrain the broader model, but because the boreholes are so sensitive to the local material properties, we also incorporated a higher resolution velocity model just in the region near the boreholes, as well as measurements of VP and VF from the logging while drilling data from the IODP expedition. So once we have our Green's functions, we just do a simple non-negative least squares inversion to resolve slip during the events. It's not time dependent, it's really just kind of a simple inversion. But I do split each event into what I've called stages to kind of get a sense at how these events are evolving through time. So now I'm going to kind of show the details of the slip distribution for each of those events. Each of the next 5 slides is going to look basically the same, so I'm going to take a second to kind of explain what you're seeing. So the plot here on the upper left is the data that went into this particular event. So this first one was from March of 2019. And so again, in pink is the near trench borehole site, orange the other borehole site, and black the GPS site. And so this is what I mean when I say I break the event up into stages. So based on changes in the slope of the data, which is me kind of interpreting that something different is happening during the event, I kind of break the event up into chunks that I then perform an inversion on. And that just kind of helps us get a sense of how the event is changing through time. So yeah, the x-axis here, time, and then pressure or position for the data sets. Moving to the upper right plot here, the x-axis here is now distance from the trench, with 0 being the trench, and then increasing landward this way. And then this is the slip magnitude here. And then just for reference, this little cartoon is showing some of the major structures in Hikurangi. This is at the same scale as this plot here. And so for this event in 2019, this is the largest event in terms of slip magnitude that we observed during our 5 years worth of data. It lasted about 150 days and peaked at around 12.5 centimeters of slip in this region that's kind of 40 to 50 kilometers away from the trench. Moving on, and just to show how well we're fitting the data, there's still improvement, a little bit room for improvement in our models, but we're kind of recovering the signals in particularly the borehole observatories pretty well. Our next event occurred in December of 2019. This is a bit of a wacky event, but you can see that in the initial stages, it kind of initiated in this bimodal distribution, and then as the event progressed through time, you can see that it kind of filled in that gap there, significantly smaller in terms of slip magnitude compared to the previous event, but similar duration when compared with that other 2019 event. And then again, this is kind of a weird event. The data our models aren't recovering the data quite as well, but still kind of gives us a good sense of what's going on. Next, kind of skipping over to an event that occurred in June of 2021. This event is a great example of a slow slip event that kind of initiates in this 40 to 60 kilometer region from the trench and then propagates out towards the trench as the event progresses. This event lasted a lot longer than the other events that we have looked at so far, but does really show very nicely this kind of propagation from deeper to shallower in the subduction zone as time went on. And then the last spontaneously occurring event occurred in June of 2022, and despite its much smaller slip magnitude, also shows this nice progression of initiating deep and then propagating out towards the trench as the event progresses. So the last 4 events that I showed all occurred spontaneously, much like many of the other events that have been documented in Hikurangi before. Going back to 2021, to that March event that I mentioned, so this spike in the pressure data here, that is that magnitude 7.3 East Cape earthquake. And we can see that now that we're kind of zoomed in on the data set here, this really dramatic pressure increase, 15, 18, and then a bit of a signal at the other borehole site. But again, kind of emphasizing here that nothing was resolvable at any of the GPS sites on shore, and even in the seafloor pressure at the borehole wellheads, there wasn't really anything resolvable except for these 2 borehole pressure records. So just to kind of emphasize the importance of these data sets for understanding what's going on. And so this event is different. You can see that it initiated right out near the trench and then made its way landward, but then still kind of concentrated in this region that is much shallower compared to the events that we've been looking at before. It also lasted not nearly as long. It only lasted about 40 days compared to over 100 days for all the other events. So if we put that all together and kind of compare these spontaneous events to the triggered event or all of the events together, so we see here the dashed line is that triggered event that I just showed. The teal is the cumulative spontaneous events, so the previous 4 that I had shown. And then if you add the 2 together, that's this darker blue line here. And I'll kind of wrap it up because I know we're short on time. So basically, we see that the spontaneous events initiate deeper and then make their way out towards the trench. By contrast, the triggered event seems to do the opposite thing. It initiates at the trench and then propagates deeper and then stays shallow for the duration of the event. The triggered event is much shorter compared to the spontaneous low slip events, but also just thinking about these events in Hikurangi generally, the borehole data show that these events last a lot longer than we had previously thought. We used to kind of canonically say that they lasted 3 to 4 weeks, but the borehole observatories are showing that really they continue going for over 100 days. And in the region less than 60 kilometers from the trench, so in the shallowest portion of the megathrust, we see that these slow slip events accommodate most of the plate convergence budget. So this dotted line here is the plate convergence budget. The plates are converging at about 5 centimeters per year here. So over the 5 years of data that we have, these events have accommodated almost all of that budget. And in particular, the triggered event was important for filling in the gap from these spontaneous events. So I will leave it there, and thank you so much. Happy to take any questions.